We're going to talk about something called direction fields, also sometimes called slope fields, and I'll use the two phrases interchangeably today. And so if we look at this first example, this will help explain why we would think about slope or direction fields. So this example here is not separable. If you try and separate the x's and y's, you're not going to be able to because of that addition in there. You might think, well, let's FOIL this out, which would give us x squared plus 2xy plus y squared. That certainly we cannot get the x's and y's separated and solve this as a separable differential equation. And the only types of equations that we know how to solve so far are separable differential equations. So we do not know how to solve this differential equation. But it would probably be nice to understand how solutions of this differential equation behave. Maybe it's one that we got by doing some kind of experiment in a physics class or something. So we still want to understand this differential equation. And the cool thing is that we can actually visually, graphically understand these, even if we can't solve them. And that's what a direction field will allow us to do. So with a direction field, what we're going to do is just find the slope at a bunch of points and draw tiny little line segments with the given slope. So let me rewrite my differential equation up here just so we can see it on the page. And so I've given you a graph below. Well, I can't even see my direction field. There we go. I've given you a graph below with a bunch of points labeled. And so what you might notice is that these are at 1/2 and these are at 1. So I've given you a bunch of points and you're going to need to grab a calculator for this, which I will as well in just a second. But what we are going to do is we're going to pick one of these points, pick our favorite point to get started. So maybe the point 0, 0. So this is x is 0, y is 0. We're going to plug that point into our differential equation. So the derivative at that point, so at the point 0, 0, the derivative is 0 plus 0 squared, which is 0. Okay, so what this is telling us is that the slope of our solution at that point is 0. So what I'm going to draw is I'm just going to draw a tiny little line segment, excuse me, that has slope 0 at that point. And what I'm doing when I'm doing that is essentially drawing the tangent line at that point. I'm just drawing a tiny little line segment up to the tangent line. Okay. And so if you think about it, a solution that goes through that point is for just a brief second going to have slope 0. So that's why I'm just drawing a tiny little line segment. Maybe, and sometimes we draw them just a little bit bigger because we don't know what else is happening. Okay. And so we're going to do this at all of these points, which could get kind of tedious, but let's do it. So maybe let's pick our next favorite point. This point up here is 0 for x, 0.5 for y. This point is 0 for x, 1 for y. Okay, so when I plug these into the differential equation, when I plug in 0, 1/2, and we're not going to do all of these calculations up here. I'm going to get 0.5 squared, which will give me 1/4, 0.25. And so now I need to draw a tiny little line segment with slope 0.4 or 0.25, sorry. So that is a very, I'm not going to do it like that. That is a very shallow slope. It's not very steep at all, but not 0. So maybe something like that, maybe a little less steep. There we go. Okay. When I plug in the 0.01, I'm going to get 1 squared. So this is going to have slope 1 at this point. So that's 45 degrees. There we go. Some of these are easy to do with the ruler. Okay. And so I'm just going to keep going. Like I said, this is going to be tedious, but that's okay. So down here at negative 0.5, since I'm squaring things, this is still going to have a slope of 0.25. So that's still going to have the same slope as this one up here. So just another narrow slope, very shallow slope. At -1, I'm going to get slope 1 again. Okay. And then we're just going to keep going. So let's see. Pick some of my favorite points. When x is 0.5 and y is 0, we're still going to get 0.25. Same over here. Then we're going to get 1 at these places. So if you don't believe me, you should tape these into your calculator and double check, remembering that we're plugging everything back into the differential equation. What we're graphing is we're graphing something that has that slope. Okay. So now let's see if I put this point here is 0.5, 0.5. When I add 0.5 plus 0.5, I'm going to get 1. So this has a slope 1. Okay. Whoopsie, slope one. My calculator's not handy, so I'm trying to do the easy ones first. So negative 0.5 and positive 0.5 are going to add to give me 0, so that's going to have a slope 0. Same thing over here. And same thing up here. Along that line, y equals negative x, the x and y values are going to add to 0, so we're going to get 0 out of our differential equation, so our slopes are going to be 0. So when I get up to this point, over here, 1 comma 0.5, I'm going to have 1.5 squared, and I should be able to do that in my head, but I'll grab a calculator. That's going to be 2.25. So this is a pretty steep slope. So this is much steeper than any of these other ones we've had. So let's remember that this was slope 1. So 2.25 is going to be pretty steep. 1 plus 1 up here, this is going to give me 4 for my slope. So that's going to be like a super steep slope. I'm probably over exaggerating things just a little bit, but that's okay. This one here is again going to be the same as this one. So try and graph this try and graph this the best we can, something like that. Okay, see, what else are we going to get? This quadrant down here is going to be the same as the top right quadrant, as quadrant 1, because everything will just end up becoming positive when we square things. So I'm going to get something like this, and then this one's going to be my super steep slope of 4, and then these are going to be my pretty steep slopes of 2.4 or 2.25, sorry. Okay, so then over here, I'm going to have negative 0.5 plus 1 is 0.5 squared, so I'm going to get 1/4 out again here. So this was just a very narrow slope, not very steep. And then I'm going to have negative 1 plus 0.5, which will give me 1/4 again as my slope. These line segments should all be about the same length. So the length of the line segments I'm drawing, if I'm drawing them as different lengths, that's just me being messy. So like I said, these are kind of tedious. So back up in this other quadrant, I'm going to get 1/4 again for my slopes. Okay, so I get something like this. So that was a lot of work to get to something that looks kind of funny, but this is our direction field. So our direction field is showing little line segments with slopes that correspond to the slope of the tangent line at each point. And so what could happen is if I know something like I know that my solution passes through a particular point, then what I can do is I can kind of follow the shape. So you can kind of notice that this has this kind of like curvy shape to it. So maybe if I wanted the solution that passes through this point, what I do is I follow the direction field lines. And so maybe the graph looks something like this. It's a little bit hard to tell because I don't have a lot of lines on this graph, but if I had more lines on my direction field, then we could draw the solutions. And that's actually what I'm going to do on the next page. So I'll come back to that box in a second. So this next page, this is just a computer drawn version of the direction field that we drew on the previous page. You can still see kind of that S-like shape. And so here, I want to sketch the solution to the differential equation that passes through the point 1/2, 1/2. So let's find that point. So the point 1/2, 1/2 is maybe up here. And so if I'm going to sketch the solution that passes through that point, what I'm going to do is I'm going to follow those little line segments. And so looks something like this, and then I follow them back the other direction, maybe something like this. So this is what that solution looks like. So without being able to solve this differential equation, we can still see how these solutions behave. Like it looks like as t approaches infinity, these go up to infinity, and then they kind of flatten out for a little bit and then go down. So if this was telling us something physical, then we would be able to understand the solution just from this differential equation. Okay, so in general, or just from this direction field, sorry. So in general, a direction field is just what we get by drawing short little line segments with the slope from the differential equation. And again, we use the word direction field and slope field interchangeably. Okay, so let's do one more example in this video, and I know that these are tedious, but they're kind of fun. So we're, in this case, our differential equation is negative xy over 2, and so I'm going to draw them at all the points that I've given you here. So let's see, if x is 0 or y is 0, then y prime will be 0. So x is 0 along here, y is 0 along there. So at all of those points, the slope of our solution will be 0. So our direction field will have small line segments of slope 0. So we can very quickly fill in a bunch of points here. And sometimes this is, like look for the low-hanging fruit, look for the things that are easy to fill in, okay? So now let's focus on what happens if x equals 1. So if x is 1 and y is 1, then we're going to get negative 1/2. So that's going to be something that has a negative slope and points that direction. Okay. Then if x is 1 and y is 2, we're going to get negative 1. So slightly steeper. And then we're going to get negative 3/2. So steeper, but still negative. So something like this. Okay. And now let's focus on what happens if x equals 2. If x is 2 and y is 1, then we're going to get negative 1. So same slope as there. Then we're going to get negative 3/2. Then we're going to get negative 3, so even steeper, okay? And then on the opposite side, we're going to get the same values, the same steepness, just positive numbers, because now x is negative, which is going to cancel our negative sign out. So you can double check, but we're going to get just the kind of a mirror image of all of these. And again, it's hard to draw like perfectly steep, like the perfect slope, but we're just trying to do our best here. Okay. So we notice that this next example is asking us why this graph, why this parabola cannot be a solution to the differential equation that we had above. Well, if we look at the direction field that we have above, things are going down. We don't have, like, this side of the equation has positive slopes, but over here we have negative slopes. So that would be a good reason to explain why that could not be a solution to the given differential equation. If we tried to follow these solution curves, what might be happening here, like if we started with a point up here, looks like it might flatten out. It's a little hard to tell that that's going to be the case. We would need a computer generated version again, probably to really tell what's happening. So yeah,